Okay, sorry about that. Had to finish up a good meeting. But super ready to go now. Can I get some hellos here? Hey guys. Hey, it's me, your favorite math teacher, Mr. Abundus. Abby's always the first. Hi Abby, how you doing? Good to hear from you. Hi Shada, hi Leo. Where's your gas mask? I determined today was not a high-risk day, but if at any point throughout the stream I determine that the risk factor goes up because I'm worried about one of you guys infecting me through the internet, then I'll put the gas mask back on for sure. All right, I will do what needs to be done. I know. Darn. Wait, did I ever put the mask on in this class? Like actually during this class? No? Oh, okay. Maybe I will then towards the end. You guys haven't gotten to experience that yet. All right. So again, sorry for being late. But let's continue on. So a bank account compounds continuously. Interest rate is 2.1%. After 5 years, the account is $6,400. How much money was there when the account opened? All right. So the first thing, if we're talking about compounding continuously, then we do want to go ahead and still use this growth formula, right? The growth and decay formula. Now, if we talk about compounding, oops, not T. If it talks about compounding like monthly, if it would let me write monthly, or it says it compounds weekly or annually or whatever, okay. Annually, then we would use this formula. But since we're talking about compounding continuously, then we are using just our exponential growth and decay formula. So, K, 0.021. After 5 years, so I know if I plug in 5, the account will have $6,400. And the initial amount, I don't know. Okay, that's what we're trying to figure out. So this is actually slightly different from what we've done before. All right, so let me set up my formula. A of t equals A0 e to the k times t. And specifically, I'm going to use this information. So if I plug in 5, oops, sorry, not t, 5. So if I plug in 5, I know this will equal 6,400. So we don't need to do like our natural log or anything like that because we're just trying to solve for A0, right, the initial amount. So the important thing to keep in mind then is that this, while it is weird and, you know, e to the 0.021 times 5, it is just a number. Okay, so if I have a number times A0 and I want to solve for what A0 is, well then great, I will just divide this number on both sides. That way it will cancel, just leaving me with the initial amount. So let me actually do the calculation. So 5762 and 8 cents. So initially, there must have been $5,762.08. So using our same formula, but a little different method in this case, to divide, to find the initial amount. All right, so most of you, I got your final vacation work, so that's awesome. Thank you so much if you did that. If you haven't, please make sure to get that to me as quickly as you can. There's still a small handful of people that I'm missing it from. So, and again, check with your friends and stuff too. Help me out a little bit to spread the word. Say, hey, did you turn in that to Mr. Abundis? Especially the people that you know don't follow this live, which is absurd because you would think everybody in their right mind would just wait around all day for college algebra live stream. I know I would. But today we will go on to logarithms. Okay, well, we already talked a little bit about logarithms. We kind of did the basic introduction of what they are. We know they're the inverse of exponentials so that we could use them to solve equations. Like we use natural log a lot to get rid of e. All right. So let's kind of delve back more into it. Now, the good thing about today is 94% of it you already learned in Algebra 2. Okay, so now do you actually remember it? I find that people often don't remember it, but it is something you've talked about before, so hopefully it comes back to you quickly. So firstly, just the graph of logarithm. I'm actually first going to graph a to the x. So you might remember whenever we did exponentials, we graphed this function and it had these points. This is a to the x. So it looked like this. Again, this is not the logarithm graph. This is the exponential graph. But hopefully remember, and I just said it actually a minute ago, logarithms are the inverses of exponentials. So if we think back to whenever I talked about inverses, or we talked about inverses, and you guys did this on a performance task actually, of how do we graph an inverse? Well, we just take the points and flip them, right? So instead of 0, 1, I have the point 1, 0. Instead of the point 1a, I'll have the point a1. And instead of the point negative 1, 1 over a, I'll have the point 1 over a, negative 1. Okay, and so this graph will look something like this. You might also remember that inverses are reflections across this line, y equals x. So that's another good way we can sort of think about how the graph would look, and we can see, yeah, since my picture is so perfect, it would perfectly reflect over that line. Okay. All right, let's talk about, so I think this is the one spot that might be new to you, is using a change of base formula. And it is this. If I have a log base a of b, and and I don't know what the heck this is. You know, if I don't know how to calculate this in my head, but I still want to know the value, I could make it easier on myself by using a change of base. So which means I could do this. I could change it so it's natural log of b over natural log of a. And so what this would be doing is changing it to base e, because remember, natural log is base e. Or if I wanted to, maybe I could do this. Well, not maybe. I can do this. I could change it to common log. So common log, we remember, is base 10. So I change it to base 10 by using common log of b over common log of a. And these would be probably the most common ones we'll use, is natural log or common log, but the point is the same. I could change this to any base that I want. If I wanted to change this to a base 137, because that's just my favorite number, I could do that by doing log base 137 of b over log base 137 of a. It doesn't matter which logarithm we choose, but the point is, how do we know what to put on the top, on the inside? That just comes from whatever was originally inside the logarithm. And then the original base, so base a, whatever it was, is then, that is the number that goes inside the logarithm in the denominator. Again, we will use probably natural log and common log the most, because those are the easiest. A good reason for doing this is just so that we can use our calculators to quickly do something. So let me bring out my calculator for a second. I'll move it over here. Okay, so let's say, for example, let me not write with a highlighter. I, for some reason, want to know log base 24 of 80. And I actually want to know what the value is. Maybe, maybe I'm doing a word problem, so I need a decimal. Well, is there a way to just type that into our calculators? Yes. Is it annoying to type in? Also yes. Okay, so instead, we could say, well, let's just change the base to something else. So like natural log, for instance. So natural log of 80 over over natural log of 24. Okay, so in my calculator, I have natural log of 80 divided by natural log of 24. So 1.379. It just makes it easier for us to type in. I truly don't even 100% know what the official way to type log base 24 of 80 is. Maybe in math. Log base. I don't know what that is. Maybe. Potentially. Let's go over. Yeah, I don't know. And that's my point. I don't know how to do it, and I don't care. I don't need to know how to do it because I do know how to use the change of base formula. Is it the log base thing? Okay, great. But I'll never remember that. I'm sure someone told me that because it's faster for me to just do a switch of a change of base formula. So again, let's say log base 17 of 3. Okay, well, same thing. I can change the base. Let's do common log this time for no reason other than that that's just what I'm choosing because I can. So I'll type it in. Common log of 3 divided by common log 17. Boom. .388. Okay. Now there are other reasons we'll use this change of base. However, this is kind of one of the more common reasons. But it'll also help us simplify some stuff, and I'll show you. I think I'll show you an example of that tomorrow. So yeah, we can change the base to whatever we want. Sometimes we'll like to have a base of 2, or sometimes we want to have a base of 10, or whatever it is. So if we need to, we can change it. All right. All right, so on to our log properties. So these are the things that you've talked about in Algebra 2. But again, do you remember them? Who knows? So the first property tells us if we have two things being multiplied, if we have two things being multiplied, so we just choose whether it's natural log or common log. Yeah. Either way, you would get the same answer. So actually, let me pull that back up because that's a good question. Okay, so let's say I'm just going to pick numbers. Let's say I do natural log of 2 divided by natural log of 6. Oops. 0.387. Okay, great. Now let's see if I do common log of 2 divided by common log of 6. Same exact thing. So it's totally up to you. Unless the problem specifically says like change to this specific base, then yeah, if you're just doing a calculation, choose whatever you want. So still end up with the same value. Okay, so back to this. So my properties, if there's multiplication going on inside the logarithm, then one property is we can split it up into their own individual logarithms using addition. Right. Or vice versa. If I start with two logarithms that are being added, I can combine those together by multiplying them on the inside. Second property, if we see that there is division going on inside the logarithm, then we can split that up into two logarithms using subtraction. And then last but not least, if we see there's some coefficient of the logarithm, what we could do is we could move that up into an exponent for whatever was inside the logarithm. Okay, so some nifty little properties that are going to help us do various things and solve some types of equations. Yeah, hopefully these are vaguely familiar. Vaguely. If not, okay too. We'll figure it out. Okay. So we have two specific things that we can do. All right, one, we can expand the logarithm. Right? If I want to expand it, I want to split it up as much as possible. Okay. Now, before we start using our properties, let's first look to simplify. right? If it's possible. It might not always be possible, but sometimes it will be. So for example, I first see a 2 in the numerator and denominator. Okay, great. So those will cancel each other out. I next see that I have a y to the 4th over y. Okay, so I'm going to simplify this. Y to the 4th over y simplifies to y cubed, right? 4 minus 1 is 3. And so now in the denominator, all that there is the z, because the 2 canceled. Y to the 4th over y simplified to y cubed. So this blue logarithm is what I'm going to focus on expanding. Right? Make your life a little easier by doing simplification at the beginning. It'll save you some steps throughout and at the end. So we have a couple options. So using our properties, remember our properties are about if there's multiplication inside the logarithm or if there's division inside the logarithm. Well, right now I have both. In the numerator I have x times y cubed. There's a numerator and denominator, so that's division. I say the best way to go about it is to first deal with division. All right. You don't necessarily have to, but I think it's a good way. Less mistakes can be made. All right, so first I'm going to split this up using subtraction. All right, so notice for this property, the numerator is what goes inside of the first logarithm, and the denominator is what goes inside the inside the second logarithm after the minus sign. Okay, so it's very important that that is true. All right, we don't want to mix up the order because it'll screw us up. Okay, so I did one split. I expanded a little bit. So now I want to expand again. Right, so now I'm looking at this logarithm because there's multiplication going on inside of there. So I know that if there's multiplication on the inside of a logarithm, I can split it up. So the first thing being multiplied, x, plus the second thing being multiplied, which is y cubed, minus log base 4 of z. Okay, so we split this up now into 3 distinct logarithms. And I just have one more step I can do, which is, so using that last property we talked about, if I have an exponent up here, the properties tell me I could move that down as a coefficient. So I'm going to go ahead and do that. Log base 4 of x plus 3 log base 4 of y minus log base 4 of z. So using our properties, we split it up as much as possible. That's what it looks like when we say we expand. So secondly, what we could also do is we could condense the logarithm. All right. So condensing the logarithm is going the opposite direction. Right? It is now, instead of taking one logarithm and breaking it apart as much as possible, we're now going to take a bunch of logarithms. So we have like 3 separate logarithms here. And we're going to try to combine those together as much as we can. Okay. And so the first thing I'm going to do is if a lot of times people see this divided by 3, kind of freak out. They're not sure what's going on with it. So I'm going to first just rewrite this. Right, remember, if I have like x over 3, I can think of that as the same thing as 1/3 x. So I'm going to do that same thing. So 1/3 log base 5 of y plus 4 log base 5 of t. Okay, so it flipped. What do you mean? Upside down. Like literally upside down? Or like you're saying I'm like, it's like a metaphor. Like I'm really bad at math, so it's like, wow, Mr. Abundance, this is upside down. Oh, actually, and wait, people are saying yes. My whole screen is upside down. Okay. Let's rotate. Oh, because of this setting, maybe? Oh, okay, cool. All right, so that should give it a second. It should work. All right, so yeah, all I'm saying is I took this, instead of writing it as divided by 3, okay, that's the same thing, oops, as if I wrote it as a coefficient of negative 1/3. All right, so now that I have that, we can go through and first let's take our exponents, move them up into, or sorry, take our coefficients and move them up into exponents. So log base 5 of x squared minus log base 5 of y to the 1/3 plus log base 5 of t to the 4th. Okay, so again, I just took all of these these coefficients and move them up into exponents. It's a screen tiny. What does that mean? Like, I don't understand. The smart notebook is small. Your webcam and regular screen are flipped. The notebook is where your webcam was. Oh. So it's like the... Oh, wait, so like I'm the main screen? And then the notebook is like in the corner somewhere? One of these? I don't know. Cool. Okay. Well, don't you guys think this is better? Should we leave it like this anyways? Assuming I even know how to fix it? I don't know. I'm not against it. It seems like it would be just as well. Okay, not getting a lot of positive response off that, so let's try and fix. Okay. Oh, okay. This. Okay. Now I think we're really cooking. we are blowing the roof off of this. All right. So we took those coefficients, made them into exponents. So now I'm going to go left to right here and just combine logarithms. Okay, so the first two that I'm going to combine are just these two. Again, just because I'm going left to right. So if there's subtraction between them, let me go x squared over y cubed. Oops, no, I wrote it like that. Okay, so besides that, once we have those two that are combined, now let's go through and combine those next two. Right, so, well, there's only two left, but we'll combine these two now. So when it's addition that is between the two logarithms, then we know that we can combine them using multiplication. Now this is a fraction, so if I want to think about multiplication, I can think about this as a fraction too, if I just want to put that over 1. So remember, when we multiply fractions, numerator with numerator, denominator with denominator. So x squared times t to the 4th, the numerators. Y to the 1/3 times 1 is just y to the 1/3. I'll make it match here. Okay. And there's just one more small step that I'm going to make, which is that the y to the 1/3, I can actually switch that up a little bit. Okay, because remember from our properties, if I have something to a rational exponent power, okay, we can rewrite it like this. So I'm going to go ahead and do that just for the sake of doing it, just so that we can remember and practice doing it. So log base 5, x squared t to the 4th over the cube root of y. Right, so that's the opposite direction of taking and combining, condensing together all into one. But it's using the same properties, just in the opposite direction. There's maybe one more. Okay, yeah, let's try this one more. Let's finish it off. Okay, so for our logarithm, remember first, if you can, look in here to try to see if you can simplify. In this case, we can't. There's no simplification we can do, but it's a good check to first look at. First, deal with the division. Okay, there is stuff being multiplied together as well, but let's first just deal with the division. Let's split it up that way. So log base 2 of x times root y. Okay, and actually, square root of y, I'm going to rewrite that as y to the 1/2, just like we talked about. Roots can be written as exponents. Minus log base 2 of z cubed h squared. I will again emphasize numerator is what goes inside the first logarithm. Denominator is what goes inside the second logarithm. So now I'm going to split up both of these, okay? I'm going to split them up in the same line even. So log 2 of x plus log base 2 of y to the 1/2 minus so this splits up into log base 2 of z cubed plus log base 2 of h squared. Now the important thing to remember here, okay, this is slightly different, is that we should put some type of brackets or parentheses around this logarithm. Okay, and that's super important that we do that because of this minus sign. Right, this minus sign will really start to screw stuff up if we don't put those parentheses around there or those brackets around there. Okay, because what happens is, since that whole second logarithm became that green stuff that I wrote, that negative should be applied to the entire logarithm. So what I need to think about here is that I should be distributing this negative. So log base 2 of x plus log base 2 of y to the 1/2 minus log base 2 of z cubed minus log base 2 of h squared. Okay. And we have, wait a minute. Can you guys not see me now? Or is that just on my end? No. Oh my gosh. Well, okay. That's pretty dire. I think we can, again, we just established earlier that the most important part of the stream is being able to see me. And everyone agrees. Okay, I think if I do this, okay, we should be good to go now. All right, so once we have this line of logarithms, the only thing left to do is we just have to do our thing with our exponents, use our last property. Okay. So that 1/2, that 3, and that squared, let's go ahead and move those down into the front as coefficients. So log base 2 of x plus 1/2 log base 2 of y minus 3 log base 2 of z minus 2 log base 2 of h. Now there's nothing more I can do there. So that is my final answer of the expanded logarithm.